planted. Your team has owned a user flag. Your team has cloned a machine. Warning, your team is losing availability points. May your experience lead you to victory.
Spy Monkey, actually I'm muted there, sorry. You're able to just...
Yeah, thank you.
Oh, we got you, man.
Okay, great. Let me do a retry on that. So welcome everyone to another Hack the Box South Africa meetup. I hope everyone is doing well, staying safe and healthy. Tonight we're going to be looking at some binary exploitation. So I hope everyone's ready for that. It's one of my favorite topics. It's also one of the harder topics because it can go quite deep, but I'm going to try and keep it simple tonight. So let's just jump right in. The Hack the Box binary exploitation challenges are all under this category called PWN, and PWN is sort of evolved into the name for binary exploitation. And it's different from other types of exploitation in that it targets native applications, so usually written in a language like C or C++ or Rust that runs directly on the CPU using machine code and not through like a virtual machine. Although you can probably do some PWN type challenges on intermediate languages, but it's mostly real low-level native applications. And it's to do with where there's memory bugs in the code. So a developer made a mistake in the code that lets us manipulate memory in some way to gain access to things that the application shouldn't be doing. And then typically it's a remote server, right? So it's not like a reverse engineering challenge where you've got the application locally and you need to crack it. It's actually running somewhere else, and I'm using server loosely because it could be creating a malicious image file that someone opens on their phone and it actually executes something in their phone. So it's not specifically a server in the traditional sense. So where we want to get to is basically sending some sort of crafted input somewhere and then gaining access to that. So that's really where the name comes from, is from being able to own it. So you own something by owning it. There's quite a lot of action around this sort of activity globally. There's a well-known PWN to own competition where participants try to break all sorts of browsers like Chrome browser and out of virtual machine things. And recently they've introduced the Tesla at these competitions as well. And the team top right, they called Team Fluoroacetate, I think it was 2019, when they managed to break so many things that they actually drove away by pwning the Tesla. They actually won the Tesla, and they won 5 laptops and a bank account full of money for all the exploits they showed off at that competition. There's also all sorts of it's very popular in capture the flags. And I used to watch these competitions called pony racing, where they've got 4 people at the same time. So you can monitor any one of the 4 or all 4 at the same time and see how they're approaching the challenge and just seeing who gets there first. This is not live anymore, but you can still get the videos on YouTube. But the people who published it are actually doing something else now, which is also quite interesting. And it's very recent as well, and it's ongoing. So just last week Tuesday, a patch was released for sudo, which is Linux's basically run as administrator tool. And this application is a bridge between normal users and administrators. So when this bug was found, it basically let anyone with access to a machine take over the machine as an administrator if you could execute this code. So this was found by Qualys' research team, and it was present in sudo for almost 10 years before they found it. And it's a heap buffer overflow exploit, which is sort of similar to what we're going to look at this evening, but not quite the same. It's a little more complex. Well, it's a lot more complex, but it's the same fundamental problem, that it's user input overflowing some sort of a buffer. Just quickly, listen, this list isn't exhaustive, but the type of bugs that programmers leave in code that opens some of these binary exploitations is things like stack buffer overflow bugs, which we're going to investigate tonight. Format string bugs are also quite common. Then there's various dynamic memory management issues like double freeing. So if the same memory gets freed twice, or if memory was freed, but you can still use it, or there's out of bounds reads and writes or overflows on heap. So there's quite a lot of things, and it's not limited to this. It's actually just limited to the imagination of the developer, I guess, on what they write and like what sort of holes they open. So to get into what we're going to tonight, we actually need a few skills, but I'll go through them this evening, so don't worry if you don't know how to do any of these things. So you need some basic software reverse engineering skills. You can use Ghidra or Risen or any other type of tool that lets you do disassembly or decompilation. You need some basic debugging skills with GDB or Risen on Linux, or on Windows. Immunity debugger is very popular for OCP. I also like x64 debug. And lastly, you need some basic Python scripting. Now, when you've got all of these basic skills, you'll be able to exploit basic stack buffer overflows without mitigations. I'm not going to lie to you, this gets quite hairy if you want to do more of the advanced exploits. So then you need to know assembly and some low-level mechanics of how memory works. So we're not going to go into that. We're just going to stick with the basic. It's very easy. Well, yeah, it's intuitive to go to the next phase once you grasp the basics. So that's definitely the place to begin. Okay, I've mentioned quite a few things now. I mentioned stacks and buffers and overflows and memory. So it's probably sounding quite abstract at this point, but let's unpack some of that. The first thing that happens when exe or application gets run, and I'm specifically in this case looking at Linux on a 64-bit machine, is the application gets loaded into memory. And the application itself actually sees 128 terabytes of memory in the user space. And this is called virtual memory. So it goes from a nice low number all the way up with no gaps to a very high number in address space. And this whole area is 128 terabytes. So the actual application code gets loaded into this area. It's usually the first thing that's like it. Sometimes it doesn't begin at exactly 0, but it's definitely the first thing in the bottom. Now in the application, there's other types of resources as well, but we're not going to go into that. Then the second thing that happens is it gets a piece of memory allocated that's called the stack. Now the stack is sort of a scratch pad for the current state of the application, and it's not that big. It's only 8 megabytes. The bulk of the memory for any application is in the heap, which is called, well, it's called the heap, but it's used for dynamic memory allocation. So if you say load an image in an image editing tool, the image might be loaded into heap memory, but there's going to be some address here in the application stack that just points to that actual image in the heap. So that the big data sits in the heap, but there's going to be just a pointer to it. It might just be 8 bytes that actually point to that, but it might also be a bit bigger than that, depending on how it's done. And in between, I'm saying this is empty. It's not always empty. It depends on what sort of process you're running. There's things called memory mapped files and devices, which also goes in there. But for what we're looking at tonight is we just want to focus on the application and the stack. If you want to just understand, so where does this 128 terabytes of memory come from? Well, it doesn't actually exist. It's called virtual memory for a reason. So the application thinks there's 128 terabytes of memory, but as it tries to allocate things into the heap, it's going to ask the operating system, give me a bit more, give me a bit more. And at some point, the operating system is just going to say, no, I'm out of memory. It's not when it gets close to that. It's when your physical machine actually runs out of memory. And this nice block in virtual memory, it might actually be split out. It might be all over the place on physical memory. So pieces of that all over, pieces of that might be in RAM swap files, in disk swap files, and in RAM. So it's really just the way the application sees it as a nice contiguous piece of memory that's actually like a false view, but it's all abstracted by the operating system. So we're going to be focusing on the application and the stack, and something else that's not in memory, it's the actual CPU. So the CPU's got a bunch of registers. At this point, we are actually only interested in 2 of them. We're actually only interested in the instruction pointer and the stack pointer. And the stack pointer always points to the top of the stack. So when new things are added to the stack, it usually grows upwards. And the instruction pointer points to where the code is actually executing at this point. Now, the CPU doesn't execute real C code, but I just wanted to show you to help you form a mental model of what's actually happening. It's actually going to be executing the compiled version of this, which is machine code. So when we move forward, the instruction pointer is going to move to 2, and things are going to begin happening on the stack. So as we go forward into the first executable, or the executable instruction in here, you'll see that on the stack there's now 2 additional things. So the first thing that happens when you enter a function is it pushes the frame pointer, actually the previous frame's base pointer, to the stack, and it makes some space for all the variables on the current in the current function. So there's only one variable in here. It's called compare, and it's integer, so it's usually 4 bytes, and that 4 bytes goes on the stack. It might not be exactly 4 bytes during actual execution for optimization reasons, but that's what happens. And now this compare calls another function called getCredentials, which is down here. So this is now going to make it call somewhere else, which means this instruction pointer isn't just going to go to number 3, it's going to go to number 7. But if you think about it, the CPU is actually quite dumb. It doesn't know how to get back. So the next thing that needs to happen after this function down here is run through, is it needs to get back to number 3, like line number 3. And the only real place to put that is on the stack, because it could probably put it into a CPU register, but the CPU has only got a few registers. So what if this function now calls another function, and that function calls another function, and that function calls another function? So that you quickly run out of CPU registers if you do that, and it's really inefficient. So the way it's been designed is you put the location of where you need to get back to on the stack, and then you go to that function where you want to go. So let's see how that works. So on the stack, we now have the return address, which is line 3. The stack pointer points to the top of the stack still, so that's now at the top of the stack. The instruction pointer is at line number 7. Well, not line, but the executable line. It goes into that function, which again creates a frame pointer. It creates a space for this buffer variable, which is 40 characters or 40 bytes. And so that's where that 40 bytes comes from. And if we move forward again and actually type in the password, so what this code does is it writes password colon on the screen and asks the user to type in a password. And then if the user types the correct password, it's going to actually read it into this buffer. So this area here is the buffer where that variable is. Now it's 40 bytes long. The password hunted to is only 7 bytes, so there's 33 bytes left. And then I should have actually had a little 11 down here, but this is going to do a compare, and then remove everything from the stack except for the return address just before it returns. And at the top of the stack right now is where it needs to go next. So that's really how this whole process works. So it goes to where it needs to go, it removes that value from the stack, and then it continues with the application. So the compare value that was returned by this function is 0, so it's going to say 0 equals 0, and you have access to the application. And the developer tests this, it looks good, it goes through QA, and everyone's happy, but what could possibly go wrong in this sort of situation? Well, if you looked carefully, there's this 500 over here, which says the applications should try and read up to 500 characters from what the user is trying to type when it asks for a password. And there's only 40 characters available in this buffer. So what is going to happen if we say try and add 80 characters? Well, let's have a look. I actually have the application here, so I'll show you. I think this one is slightly more than 80, but it's good enough. So here's my application. It's called password. You just ask for a password. If I say test, it says imposter. If I say hunter2, it says welcome friend. If I say a bunch of A's, the application crashes. And that's because what's happening behind the scenes. So yeah, this is just me not put in. It says that's a nice stack. Would be a shame if someone corrupted it. And that's exactly what I did. Is I just entered a bunch of A's, and it fills the buffer, it fills the frame pointer, it fills the return address. So this is where it's trying to go and return to at the end of that function, and it fills everything else because it's just that big. And when this function completes and it tries to go back to where it should be, it gets to this address and it sees, well, it needs to go here, but that's not a valid address, so the application just crashes. And that's great. So now we've got a crashing application. If this was a web server, we have a denial of server denial of service attack. So we can bring down a web service. If this was some sort of a gaming service, it's down. If it was something in your Windows kernel or operating system kernel, you've got a blue screen. So it's powerful in itself, but we can actually do something else. We can, instead of just doing a bunch of A's, we can do just enough A's. So we fill up the buffer with A's, or anything really, just some data. We fill up the frame pointer, so we don't really care about that. And then just before we override the return pointer with something that's going to break it, we say, instead of going to line number 3, where it was supposed to be going, we say go to number 4. So we bypass the actual check. So say, for instance, we didn't know the password because it might not be hard coded in an application like this. So if we didn't know the password, we might make it just ignore the incorrect password, and we go directly to the post authentication step. So that's really what you can do with this sort of exploitation. Okay, I'm going to try and demo this. This is quite tricky. But the first thing we want to do is to find out exactly how many A's we need to enter. So what we could do is run this in GDB. So GDB is the debugger. And say password, and we can say just run it. Before I do something interesting, I'm just going to crash it again. So I'm just going to say send in all the A's, and you'll see the application actually crashes, but the debugger lets us actually handle that crash and see what's going on. So you can see it's trying to return to this address, and that 414141 is just hex for A, like capital A's. And obviously that's not a valid address. Now what we want to do next is figure out where exactly in this long list of A's that is. And the easiest way to do it is to actually create some sort of a pattern where we go, let's make some A's with a lowercase a, and then some A's with a lowercase b, and some like 7 A's with a lowercase c, 7 A's lowercase d. So we can create a pattern and then pass that in, and then we can see, okay, we're seeing this thing breaks at maybe this address, and then we know, okay, that is where we need to put in the return address. There's a nicer way to do that though than just doing it in Notepad. So I have some code that so the way I like to do it is using a library called Pwn Tools, and you should all have it installed. I sent out the script, but if you don't have it installed yet, it's quite a quick install, so I'll ask Toko to just share that in chat as well. But basically, I just open Python 3 and say from Pwn import everything. If you're a Python developer, that's not a good way to import, but this is good enough for us. And then you say cyclic, and then how many characters you want. So let's say I just want 100. And then you could also do this n equals 8 or n equals 4. So 8 for a 64-bit process, because all your addresses are 8 bytes long. So you want to create this nice string, and it's going to prefix it with a B and a apostrophe. Just ignore that. Just get it from the first A. So if we go back to the debugger and we say run this again, it asks for the password. We send in our nice format string, and it says it's going, I think I broke something. Oh no, it's right. So it's saying it's going to return to that address. I usually just grab it up here because this address we're looking at is going to be at the top of the stack at this point. And I sometimes just do a sanity check because it should always be one address on from the frame pointer. So that this RBP is the frame pointer at this point. So this G and H is usually, it means that's directly after that. So then you copy this, go back to your Python instance, and you just say cyclic find. And then in Python 3, it needs to be byte. So you do a B and then paste the string, and this N value just needs to match what you had in the first time. So it says that's exactly after 56 characters. So you can do 56 A's or just some filler, and then you send in the actual address you want to use. So I'm going to stop this. I think I've pre-written this exploit, so I'm just going to show it. Actually, I'm going to break it first. So let's say we okay. Let me begin by explaining what this actually does, because this might be quite confusing. So the first line is just to make it run from the command line. We actually don't need that. I'm just going to remove that. Then we want to import the Pwn tools library. So it basically gives us access to all of these other things like elf, or at least this one, which is just loading the file. And then we could run it in a debugger, which I actually want to do. And so I've just made this template that I'll share with you. But basically, you can say, I want to run this in a debugger using this one, or I just want to run the process normally, or I want to run this exploit against a remote server, which is hosting the same application. So I always begin by debugging locally, and once I'm happy that everything's working and it's a solid exploit, then only will I run it as a process to make sure, and then I'll run it remotely. So what we're doing is we're saying let's send in 56 A's. This is I can simplify this by saying I'll just remove that just to make it slightly simpler, and say 56 A's, and you need to prefix it with this B just to make it bytes. And then after the 56, we can send in the address where we actually want to go. So in this case, we don't know the address yet. So there's a couple of ways we can go about this now. We could say open it in Ghidra. So Ghidra can actually tell us, well, if we want to go to this line, welcome friend, we need to go there, because this is going to put the welcome friend code into the address or the RDI register, and then it's going to call the puts function. So we can't just call the puts function with nothing in the RDI register. We actually want to have that text in there, but it depends on what we want to do. It might be good enough to just jump there, because that's also in this if block, but I actually want to show how this works. So this address is 4011B9, and that's basically what I had in this in here. So there's something Pwn Tools gives you. It just formats that correctly for a 64-bit address, and then it adds it to our buffer, and then we can actually send that to the application. Before we send it, I just added this code. You don't need to use it, but it just writes it to a file called message.bin, so that I can have the exact buffer that was sent to the that was sent to the actual application. So let's see what happens if I actually run that now. So this is the bypass one. So I removed it from the. Can't run it automatically, so I need to run it as exploit bypass.py. So what I did is I removed that first line, which actually tells it how to execute. So because it doesn't know how to execute, I need to tell it to run Python and the script. So that should run it now. So in there, it's going to, just want to make the screen a bit smaller. There we go. So we're actually in the check credentials function at the moment, and now this is proper debugger land. So in the debugger, we can type next in next or just n to just go to the next instruction. So it should go from this instruction, which is, so this is the actual machine code. It's going to go from 401.263 to the next line, and we can go on like that. So it's going to push the frame pointer to the stack, and then it's just going to continue. So I'm just going to skip forward. So at this point, it's going to write out password, but it's not going to let us enter something yet. And at this point, it's going to read up to 500 characters. And I automated that, so I don't need to fill it in. But it actually completed it. So you can see there's a bunch of A's, but it's actually not overwritten the return pointer with the A's. So you can see this return pointer is actually pointing to that address we wanted it to go to, 401.1B9. I think that was right. Yeah, 401.1B9. And then that should actually make it do the login. I suspect I actually modified this application. Let me just have a quick look. So if I just want to see if I do this message and I pass that to password. Yeah, I modified it. Let's just have it. I'll just do this live. So let's close this. I just want to find the new address. So the easiest way for me is actually just to check in GDB. So I can say password, and I can say info functions. So it's going to show the names of all the functions. And in this main function is actually where I want to jump to. So I can say disassemble symbol disassemble, if I can type correctly, main. And we actually want to jump to, I think it's over here now. Sorry, I recompiled this application just before this meetup, so that's why it's different now. But if you load this into Ghidra, it's going to say that's actually the address where you want to be, not the one I had just now. So let's try that. So I'm just going to open this bypass again and say that is where we want to go. So let's see if that works. Actually, I'm just going to continue and see what happens. So you can type continue and it will just continue running, or just C. So continuing. And I think this actually worked, but I did something else that's quite dumb in the script. So let's just have one more look. Exploit bypass. I'm saying print whatever is coming out of the application at the end. So the way PwnTools lets you do this is you can say, for this target application, I want to receive output from the application until I get this password with a space at the end. And then I want to continue running the rest of this code. So then you can say, I want to this target, actually send this data. And what I did at the end is I said, just print the rest to the screen. But when I'm running in a debugger, that doesn't happen. So I actually want to go back to an interactive instance. So giving control back to the user, to the actual application. So this should work now. Let's see. And if I just say continue, there we go. So it's saying welcome, friend, and press any key to continue. Just to show you that this actually works outside the debugger as well. So here's the message file it generated. So it's got a bunch of A's. So I'm just opening it in a hex editor because you can't actually see these characters at the end, because it's mostly null bytes, right? So that makes it very difficult to actually type this into application. You need to sort of generate valid addresses which aren't valid characters. So this first character is valid, it's a 1, but the other ones you can't actually type on a keyboard. So the only way to really see it is with the hex editor. So what I can do, I'll just show this before I do that. I'll show if I just pass in the password like this, it's also going to say password, and then it's going to take that input and send it to the application, and it says that's correct, welcome friend. If I say test, it says no, that's wrong. But if I send this message, which is this binary file, send that to the application, it's also going to say welcome friend, press any key to continue. So it logged me in, it still crashes. Now it crashes because I still messed up the frame pointer, I think. But we don't really care about that. We got in, we got past the password prompt. So we can probably, in a real application, this crash will actually happen at the end, I think, or we could just clean up that that frame pointer to be a sane value, then should also avoid this crash. And that's really buffer overflows in a nutshell. But let's go on with the presentation because there's more. So that's what we did just now. We said we're actually redirecting this application to go to the next place we want to go, and we can make it jump anywhere, and that's quite key. Is there's sort of an art and science to any type of binary exploitation, and the art part is you need to be quite creative with what sort of instructions you put together and where you jump and what you do at those points, because there's quite a lot of ways to do it, but sometimes it's very constrained and you need to really think outside the box to get arbitrary code execution. So we jumped somewhere else in the application, but there's more to this because we actually want to own this system now. We don't just want to bypass a check or jump somewhere else in the application. We actually want to get the rest of the system. So what the next step is actually injecting code onto the stack. So instead of just running or jumping somewhere in the application, we're saying no, let's think big. We actually want to put valid code on the stack and tell the application just return over there, and it's going to run that code. And this works because the CPU itself is quite dumb. It doesn't know about this is an application and that's heap and that's stack. It just sees addresses, and you can tell it don't worry about that, just jump over here. There's some mitigations against this now that I'll explain in a bit, but this type of attack is still very common in especially older software that a lot of people are still using, and it's definitely something you need to know for the OSCP exam if you ever attempt that. It's also quite common in CTFs and on hack the box challenges as well. So it's worth knowing about this, and it's easier than it looks. So once you did what we did previously, it's really just injecting some additional code and then jumping there. So I've got a exploit already written that I'll just walk you through. Actually, I broke it because I wanted to walk you through properly. So this first line is, again, just telling it this file can be executed with Python 3. This time I'm not going to take it out. It's importing Pwn tools again. It's saying this is the file I want to execute. And just for clarity, you don't need this, especially in this application. You actually just need to tell it where your application is. So you can just do it over here and say this is password and then just take that out. But I like to do it this way because when you get a bit deeper into binary exploitation, there's a lot of additional information you can get out of this executable with Bone tools by using ELF and all sorts of functions and accessors and things to get symbols and addresses and values out. And you can even search for things in there with Bone tools. We're not going to go into that now, but it's really powerful. I'm just going to run it as a process. Actually, no, I'm going to run it through the debugger. And we want to receive until it says password and then send in 56 A's and a bunch of B's. And what I actually want to do is to add some code in here, like actual machine code that's going to be pushed onto the stack. And then instead of going to this address, which is invalid, go to where my code is sitting. So this type of machine code that you can push onto the stack is called shellcode. And there's a really nice website called shellstorm.org that has all sorts of shellcodes. And they're not updating this anymore because shellcode doesn't quite work on modern applications anymore, but it's still works on older apps and in CTFs and in OSCP exams and so on. The new way of doing things is return-oriented programming, which we might get into in a future meetup. But there's all sorts of nice things here. So I could just grab one of these and say, I want to read a password and that's 105 bytes, or I want to. So you can basically do any of these things you want to. In my case, though, I want to actually make my own shellcode. So I'm not going to go through a shellcoding course right now, but there's a tool called Metasploit Framework, and they've got a shellcode generator called MSF Venom. And this tool has a bunch of shellcode payloads you can generate to download and execute something, or to you can inject like a VNC into the process. You can upload and execute. You can get reverse shells, and so there's a ton of things in here. We're just going to keep it simple for now and say we want to do a payload called Linux, the 64-bit version, execute. And the command I want to run is called carsay. Now I want to check on this machine. So I could basically run any command, but I want to do carsay hi there or something. Just want to see where that is. I'm not sure if I need the path, but let's say we need the path. Just want to grab that. Come on. My machine doesn't like me. Let's try that again. Okay, maybe that worked. No. Okay, let me memorize it. User games carsay. Okay, not too difficult. User games carsay, and then let's say you have been pwned. And I want this in Python format, and that should be enough. So this should now generate some shellcode that's going to execute that, and I can then just copy paste this into my script over here, like that. And if I now run this application, I'll be able to see where that is and be able to update this address when I see where it is, and that should do it. So let's try this. So let's say execute this exploit. It should crash. Let me see what's going on. Okay, so it hit my breakpoint, but let's continue. So it should crash. So it crashed because it tried to go to address B, or all those Bs, or this is the actual address. Obviously, that's not valid. Hopefully, I can copy things now because that's quite important. And for some reason, my terminal doesn't want me to copy things anymore. That's very strange. I don't actually. It's 7 with a bunch of Fs and then df10 at the end. So I should, let me see if I can. So if I change this, I'm not sure if that actually copies. Let me see how many Fs is that. 7 Fs. Okay, so df10 at the end. So that's actually where my shell code begins. So that's just the last. That's the top of the stack, but just above that. So the actually, just let me double check this. Yeah. So it's actually, yeah. So I thought it would be above that, but oh no. Okay, so it actually wrote it downwards, so it's below that. So that's the actual address. So let's try and get that in the copy. And I'll just do another window. Okay, hopefully this copied, but I doubt it because my machine doesn't like me. Okay, so we actually want to go to P64, and this is now OX7, 1, 2, 3, 4, 5, 6, 7, and DF10. That's where we want to go, DF10. And if I run that now, so this is going to run my application and firstly hit the breakpoint again. Just want to move this up again. And when I continue, it should, well, so it did a bunch of things. Let's actually, so it says you've been pwned, but that a lot of things happened there. So let's just run the message again, and there you see. So this password application didn't have this code in it that says go and do this and run this, but by injecting shellcode into the application, we managed to do it. And something I should have actually shown earlier, but what you should always look at when you're doing these types of exploits is something called checksec. So on this application, so if I just run checksec on this application, it's going to say what types of mitigations are in place. And in this case, there isn't really anything. There's this partial roll row, which isn't relevant in our case. And very important also to mention is on my machine, I just disabled ASLR for this demo, because if you don't have ASLR disabled, your addresses on the stack is always going to change for every execution. So for every execution, it's going to be different. So you can't really hard code this value. You can't really hard code this value over here because it's going to be different every time, unless you have ASLR disabled. And that's it. That's basically how to do stack buffer overflows. Before we go into a practical though, I'm going to just tell you about some of the mitigations that you'll run into, because things aren't this easy these days. So the first thing is called write XOR execute, which means what applications do these days is when they launch, that memory gets flagged as either writable or readable, but they can't be both. So this basically kills shellcode, because you can't write code into memory and execute it. You can only write it, but you can't execute it, or you can read it and execute it, but you can't write anymore. So that kills it. On Linux, the implementation is called NX, no execute, and on Windows it's called data execution prevention. On Windows, any 64-bit process has it enabled, but any 32-bit process, you have to, at the application level, either ask for it, opt in, or at a system level, force 32-bit applications to have it on. So you might get lucky and it might be off for 32-bit applications. That's why most of the challenges you'll see in certain exams are 32-bit processes on Windows, because 64-bit, I think it forces the data execution prevention to be on. And what's going to happen if we try and execute shellcode, the application is just going to die. It's just going to throw a critical error and it's going to fail. So it's not going to work. The second mitigation that's very common is called address randomization, and there's a few things that gets randomized. So address space layout randomization is ASLR. That's enabled at an operating system level, and it's on by default. I haven't actually seen a base operating system that has it switched off. But this is something that you'll run into when you do these types of challenges. Is you run your exploit in GDB, the debugger, which turns off ASLR by default, and you manage to run your code and everything works locally. But as soon as you try and run it on the remote server, it doesn't work. And you think, okay, why not? Everything's working locally. Then you need to check ASLR. You need to check that it works when you're not running in a debugger and ASLR is on your system. So that's not something that gets switched on at a binary level, although I've seen some ways you can actually break ASLR at an application level if you strip relocation tables on Windows. I don't know if that's true for Linux as well, but there are ways to actually make an application not ASLR compatible. The other thing is platform independent code. Just before I get to that, so ASLR is when when this memory actually moves around. So when you run the application, every time your application stack or your thread stack is going to be at different addresses. And yeah, that basically denies hard coding these addresses. What platform independent code execution does is it moves these addresses. So it moves your actual application code. I think it also moves your imported libraries, but that might be ASLR as well. But I think it's both of them are to do with this PIE. And this basically just prevents knowing where to return, except if you have, except if you leak it. So in our exploit, we changed this to go to 4, and as soon as we try and jump to that address, it's just going to fail. Like there's nothing there. So your exploit is not going to work when there's nothing there to jump to, and that's with PIE. Unless you can leak the address. So there's some bypasses for this. If you can actually have a way to leak the actual address of something, then you can sort of figure out where everything is based on a few references. Another mitigation that's quite beautiful from a simplicity point of view that I actually like is called stack canary. Now what this does is the developer just writes their normal code, and the compiler is going to inject some code when it actually compiles. So the developer's code goes to the normal, like goes in the function, but it gets wrapped in this logic that says, the first thing is you create a variable called canary, and it's got this secret value in there that comes from, I'm actually not sure where it comes from, but I think it's a CPU register or like some secure place. You can't actually read it from the application's memory space, and it puts it in that variable. And then the developer's code runs, and you might do buffer overflow and actually overwrite all of these things and put a very nice return address in the return address. But before this function can return and go to that address, it does this check that says, is the canary still the value it should be? And if it's not, your application just crashes. So that basically blocks buffer overflow exploits, unless you can leak the canary. So that's actually something that you do in a lot of CTFs and some of the Hack the Box challenges. Is you need to find a way to actually leak the canary value, because I think it's the same value for the whole application execution in all the functions, but as soon as you close the app and open it again, it's going to have a different value. Lastly, I need to mention another mitigation is just the compiler screaming at the developer. So just pumping out some warnings and a lot of documentation with big bold letters saying, don't do this, this is unsafe, getting your developers trained. But in a lot of companies, you need to ship software and people have different skill levels, and someone else wrote the code. I'm just fixing it. So you need some hardware and operating system level safeguards. You can't just leave it to developers. There's quite a lot of movement these days in more memory safe programming languages like Rust that limits what the developer can do, so they can't shoot themselves in the foot. But it also gets in the way of some developers who want to do things in their own way, and those languages just say, no, you can't use that. You need to talk to this way of doing things, and we'll make sure your memory is safe. That's all the mitigations, and that's the whole presentation. So before we go to the practical portion, I just want to check in with Toko if there's any questions.
No, so people have been chatting and other people have been responding, but you've had some really good remarks back from that. So I'm quite happy to take a bit of a break now if you are. Maybe get some water, people can go for a walk or something, and then we can regroup, reconvene in the Discord channel and get our hands dirty.
Sure. How long do you think?
I don't know. What are you thinking? How long do you need? You did most of the speaking, so.
I'm fine. Let's say 10 minutes.
Awesome.
Cool.
Okay. So what's that? We'll do 7:15 then. 12 minutes. 7:15 we can reconvene and.
Yeah. I'll put up a timer as well. Actually, just before we go there, let me just maybe intro the challenge, and then we just reconvene in Discord. Sounds good.
Awesome. Yeah. And if you guys do have questions at any point, just chuck them in. This sort of becomes an open discussion now at this point. So, and we encourage legal liquor now that it's open as well. And let's make this social as well. Let's make this a bit of fun.
Yeah. Okay, so let me show you the actual challenge we're going to be doing. So on Hack the Box, there's a challenge called Hex Diablos, and it's by someone called Red2Pwn, which I don't think it's their real username, because that's basically a return to a function. So when you do these challenges, you sort of learn what these things mean. So this usually means your challenge is to do a Stack Overflow and return to a function that's going to give you the answer or do the work for you. So on Hack the Box, you just go to, let me see if I've got it. So you go to Challenges, and under Pwn, you go to Hex Diablos. You can download the file here. So I think it's just a zip file. And once you have a working local exploit, you click on this begin instance button, start instance, and it should take a few seconds, and then it gives you an address. So you can use that address in this this template I created. So I've given you guys the template I made for myself to use. So you can put the application you download's name goes in there, and the remote address needs to go in there. So that's what you get from Hack the Box, because once it's working locally, you want to comment out the local debugger and you want to uncomment this line that says actually run it on the remote server. And then you just want to do what I did previously using the offset. So you want to create a pattern and send it to the application. I think this is a 32-bit application, so use the n equals 4 parameter. So this is going to generate nice a nice pattern for 32-bit applications, and then run it through GDB like I showed. So run GDB and the application name, go to the place where it asks for the input, and then send in that pattern, see where it crashes, get the address out, and then use this one to actually get the offset. So you're going to get an address or a text value that's going to be something with a bunch of A's in it, and that's going to tell you exactly how many junk characters or filler characters you need to pass in, and then you can use that and just put that number in here. And then you can maybe I should just show this application in Ghidra quickly. So this is the application you're going to be targeting. So there's the main function, and then it's going to write who are hex Diablos, and then there's a vulnerable function. And in this vulnerable function, you can see there's a buffer where it gets it from the user, so the user can write anything in there, and there's no limit, so you can write as much as you want, which is the overflow, I guess. And then it's going to write that back on the screen. But there's also this other function called flag. So basically, we need to jump into this function. So when that vulnerable function returns, we need to overwrite the return pointer to go to this function. And that's as much as I'm going to give you right now. We can take a break and then get back to this. Also, do have a look at what mitigations are in place. So run checksec. You should have it if you install the tools I sent out for this meetup. Well, I showed you now where the bug is, but have a look for yourself. So see if you can identify it yourself and find out exactly what address we want to jump to. So it's going to be in that function I showed, but you can find the address yourself. And then debug, send a pattern, find the offset, overwrite the return pointer, and then there's a bit of a twist at the end. So you need to add some more values to the stack to bypass the checks. But I'll leave that to the Discord session. If anyone finishes this early, we can also do the space challenge, which is also a normal stack buffer overflow. Some of the other ones get quite difficult because some of them you need to do heap and ROP and all sorts of memory corruption things. So do this Hex Diablos one first, and if you finish it early, let's do space together. I actually haven't done it, so I can do it with you. And I think that's it. Let's do the 15-minute break or 10-minute break, and then meet in Discord, I guess, at 20 past.
Yeah, 20 past. Just FYI though, the zip file is password protected, and the password is hack the box from their website, just in case. Awesome. Yep. 10 minutes.
10 minutes. Okay.
Sweet.
Cheers.